Okay, so in this video we're going to go over your Pelton turbine equations. So the first thing we need to sort of dissect when it comes to this turbine is, how we can modify our velocity to accommodate the moving vane. Okay, and a little bit of back step, I guess. We are going to analyze a supposed steady state where we have, basically the interaction of the stream and one vane at a time. So these equations work out pretty good if you only have one vane in contact with the stream at a time. Currently, as you saw in some previous videos, we have 3 vanes on the turbine. At one point I had 6, but I realized that the stream was hitting 2 at one time, which my math didn't really account for. Okay, so basically we have to figure out how the moving vane is affecting the velocity delivered to the vane itself. Okay, and as we did with the static case, we're going to assume that the velocity going into the vane is the velocity going out. As we all know, there should be some frictional effects, and it should effectively create some losses and maybe slow the flow down a little bit. You'd lose some energy, but we're not going to assume that for this case. Okay. So the velocity delivered is going to be the velocity of the stream. Okay, so we made the nozzle the same dimension for this as we have for the static impact jet, which will be 10 millimeters. In some previous videos, I used the 0.375 millimeter diameter one, but in current labs, we use the 10 millimeter one, which is the same as the one on the Pelton turbine. Okay. So yeah, you'll be able to, when you know the volumetric flow rate, that's Q dot, you could divide that by the cross-sectional area of your nozzle, and you can find the velocity of the stream, okay? So yeah, pretty simple stuff there. You have the velocity of the vane, however, which kind of gets a little bit complicated, all right? So if you look at this diagram, I only have two vanes drawn on the turbine. There should be a third, but anyways, the vane is going to be moving sort of rotationally, all right? And we're going to say that the horizontal component of its rotational velocity is going to be equal to omega, which is the small w, okay? Later on we'll talk about work, that's the big W, but let's not get ahead of myself. You have omega, which is small w, times r times cosine theta, okay? So theta is the angle taken from vertical here. Okay, so when theta equals 0, okay, that's when this equation is sort of maximized, which makes sense because at this point here, it'll have the most sort of velocity in the horizontal direction, which is the direction of the stream. Okay, so yeah, we could take from the static case our forces. Okay, so it was rho v a times the quantity cosine beta plus 1. Okay, so this gives you your force, all right, and you have sort of 2 components, the thrust component and the impact component. Okay, so when I drive these equations, I sort of kept those values the same for the other one. So this particular velocity in the old lab, well, we still use it, but in the static lab would be considered V1, okay, and that's the velocity as the stream hits the vane, okay. With us, we're going to change that velocity to V delivered, okay, and we're going to apply that to our model here, okay. So things kind of change kind of drastically as as it rotates through the angles, okay? The thrust component, for instance, is always going to stay mathematically perpendicular to the radial vector, okay? So this is the radial arm, okay? The vector coming out of it. Basically, the thrust vector is always going to be perpendicular to that radial vector, okay? Which makes it kind of easy when calculating torque, but the impact component is only ever going to work in the horizontal direction, okay? So that's along the direction of the stream. All right, so I decompose them. When you apply a force on a lever arm, you create a torque, right? And the torque is what we're going to use later to find the work done, okay? So anyways, I kept them separate, so you have the torque from the thrust is down to the force of thrust times R. And again, that F thrust is always going to be acting perpendicularly, or at least that's our assumption, as it goes through its rotation. So, yep, next we'll decompose that. We have, that's V delivered squared times rho times A times cosine beta times R. Okay, so again, first time we've seen one of these cosine terms, that beta is the angle of the vane. Okay, and for the static impact jet, it's going to be 60 degrees. That's the new one I'm using. There'll be videos on that to come. And then for the Pelton turbine, we're going to say that beta angle is 30. Okay, so anyways, so beta angle is 30. Now I can decompose this further, okay, and what I said up here was the velocity delivered is V sub s minus u vane, okay, and u vane is very simply omega r times cosine theta. Okay, so V sub s minus omega r cosine theta, that term is what the V delivered turned into, okay? And then you'll square that whole term, times rho times A times cosine beta times R. Okay, so that's our thrust component, pretty clear. Now we have the impact component. This one gets a little bit confusing. We kind of lose a beta term, right? Because the thrust is what's dependent on the blade angle, the angle at which the water is shot away from the vane. But the impact component, we'll actually add another cosine term. So we have the torque from impact is F impact times R times cosine theta, okay? And if we remember from our static case, that's just the one component in our parenthesis, and so your impact force ends up being rho times V squared times A, okay? Which is in the form, again, m dot V. Anyways, we end up having that, for this case, be V delivered squared times rho times A times cosine theta. Okay, so we could decompose that even further, and yeah, we have our V sub s minus omega r cosine theta term. Okay, so this term here, I haven't fully decomposed it, right, because I still have the parenthetical squared term with the V sub s minus omega r cosine theta, but you have another cosine theta term over here where the thrust component above it does not have an additional cosine theta, it has the cosine beta. Okay, so anyways, what we're going to do is we're going to take the integral of this torque, okay, and then we're going to set it equal to the rotational work done. Okay, so basically we're going from negative pi over 6 to pi over 6. That's when the vane is first struck by the stream, and then when it leaves. Okay, so this is what we're going to call negative pi over 6, and that's what we're going to call positive pi over 6. So yeah, we're taking the integral of the thrust component, which I've explained up here, plus the impact component. All right, and then the rotational work is very simply half I omega squared. Okay, so I give you I calculate that myself, and then you have omega. All right, so what you'll then be able to do is set these two equal to each other. Now, I know you have a couple of variables here, right? You have omega, beta, you have theta, all that sort of jazz. You have, your R's. So pretty much everything here is known apart from omega. Okay, so the theta is within the definite integral. So the way I set this up was in MATLAB, okay, and I kept omega a symbolic variable, all right, and then I had it solve for it, okay. You could do all of this by hand. You could do this integral by hand. It's not that hard. You end up with a cosine to the third term over here, which you have to decompose with some trig identities to integrate it, but you're perfectly fine to use MATLAB like I did. So yeah, you'll set this term, the work done by the vane, equal to the rotational work, okay? And they'll both have omegas in them. You can mix things around to then solve it with your quadratic equation. But yeah, again, I had MATLAB do it. And then you solve for omega. Yeah, and you're able to compare that to what you have experimentally. So anyways, these are the equations for the impact for the Pelton turbine. And all of this is, again, in your lab manual.